Hi, everybody. In our last video, we talked about the periodic table and the structure of the model of the atom and what makes it up. And we referenced the concept of an atomic mass. And I talked about how on your periodic table, they're all recorded with a certain decimal value. And the reason for that is the term that you see on the screen, and that's called an isotope. And an isotope refers to atoms that are the same element but have different masses. Okay, so it's important to remember that isotopes have the same atomic number, but a different number of neutrons. Okay, isotopes are still chemically the same, they just weigh a different amount. Some might be a little bit lighter, some might be a little bit heavier. And so there's really two terms. There's the atomic mass, which refers to the average of all of the isotopes, which is why it always usually ends with a decimal value. And then something just called the mass number, which is the total number of protons and neutrons, just like the atomic mass, but this one is specific to one isotope. So when we used the element shorthand in the last video of carbon-14, that was one isotope of carbon, but the average of all of its masses on your periodic table is 12.01. All right. So if we practice writing out different isotopes, like in the example problem over here to the right, it says that there are three isotopes of oxygen, oxygen 16, oxygen 17, and oxygen 18. And if we were to sketch out each isotope, we would start by drawing the element shorthand, the symbol O, to represent oxygen. And after we located oxygen on the periodic table, we would see that it is the 8th element. So its atomic number, which goes in the bottom left corner, is the same because they all represent an isotope of oxygen. All right, the first isotope is going to have a mass number of 16. The second isotope is going to have a mass of 17. And then the third isotope is going to have a mass of 18. All right, so from that shorthand alone, after we had the last video and completed that PEN worksheet, we should know that that means that this oxygen atom has 8 protons, 8 electrons, but this particular oxygen isotope, 16 minus 8, means that it also has 8 neutrons. This one would have 9 neutrons, and that this one would have 10 neutrons. Okay, so more of the packing peanuts filler material in the nucleus, making each isotope slightly heavier than the next, but it still is going to chemically behave the same way as any other oxygen atom. Again, the reason that we draw the larger mass number over the smaller atomic number is that it's already drawn that way to set up a subtraction. 16 minus 8 equals 8, 17 minus 8 equals 9, 18 minus 8 equals 10. Okay, so it's just a quick way for us to visually get a glimpse of the atomic structure of that particular isotope without actually having to draw out or scratch work out each individual piece. Okay, oops, smartboard, not smart. So when we talk about those different isotopes, each one occurs in nature with a different relative abundance. Okay, and that is essentially a fancy statistics word for a percentage. Not all isotopes occur in nature with the same amount in existence. The average atomic mass is always a decimal form mass that's recorded on your periodic table, and it's in reference to how much abundance each isotope occurs in. So if we look over here to this copper problem, it says that the element copper has only 2 isotopes, a mass of 63 and a mass of 65. And the abundance of copper 63 is 72.4%. Okay, so percentages are always based out of 100. So that means that a large majority of copper in existence has a mass of about 63. Right? What would the relative abundance have to be for the other isotope if there's only 2 isotopes in existence? Well, the remaining 100% has to belong to copper 65. So then that would be, let's see, quick mental math, 27.6%. right? So in total, all of the isotopes add up to 100% of the existing copper in the world. And so there's no like uh, memorization of this. You'd have to be told your relative abundances. So I don't want you to get too bogged down into these numbers. But what we can infer is that if copper 63 has a larger relative abundance, then it's a pretty good idea that if I took 100 random atoms of copper and put them into a bag and I reached in and pulled one out, I have a pretty larger percentage or greater chance of pulling out a copper 63 atom instead of pulling out a copper 65 atom. Kind of like in Vegas. If I had to bet on one atom, I would bet on the occurrence of copper 63 being the one that we use. All right, but since we don't have any way of pulling one individual atom into a chemical reaction and zooming in on it to see how many neutrons it has in its nucleus, we can only go with the assumption that we probably have an average mass of all of the different isotopes occurring. So what is an estimated average atomic mass for copper? Well, in terms of an average, that's you adding up all of the parts that you're going to take the average of and dividing how many people or how many parts you have in there. So like if I took an average age of all the students in my classroom, I'd add up all your ages and then divide by how many students are in the room. The average has to fall somewhere between 63 to 65. All right, I wouldn't take the average of all the high school students at Waubonsie and then wind up getting an average age in the 30s. Okay, so it has to fall within the range of the two masses. And if most of the weight is being contributed from that 72.4% of the smaller copper atom, then my average mass is probably closer to 63 and maybe 63.5 something. Okay. And if you find copper on your periodic table, it's in the top row of your transition metals, you'll see that copper's recorded atomic mass is actually 63.54. Okay? So that holds true with what we know of the percentages in reference to the two copper isotopes. Mostly copper 63, so the average mass is going to be pretty close to 63. Okay? So how do we actually calculate an average atomic mass? It's just like you taking the average of a bunch of numbers in a math class. We're just using the percentages to account for how many pieces we actually have. Okay? So the first thing we're going to do is convert the percentage to a decimal. Okay? So we've got 20.6% of this bromine isotope that has a mass of 79. And then we've got 78.2% of this isotope that has a mass of 80. And then we've got only 1.2% of the last isotope that has a mass of 81. So to convert the percentage into the original decimal form, all we have to do is divide each of these by 100. This takes us out of the average mass of 100, the percent of 100 different atoms, down to just one individual atom. So this is going to equal 0.206, 0.782, and 0.012. Okay. Now that we've got them into decimal notation, we're going to multiply the decimal by the mass number. And we have to pay a little careful attention because this percentage, 20.26, was connected to that atomic mass of 79. Or I should say the mass number 79. And I want to talk a little bit very briefly about what this AMU stands for. That's just a generic unit, like grams is a unit, meters is a unit. When we're talking about atomic mass, we use AMU and it stands for atomic mass units. Okay? So we're going to say 0.206 and multiply that by the mass from that original percentage, 79, and then 0.782, multiply that by, oops, not 79, by the mass that's connected to over here, 78.2% had a mass of 80. And then the last one, this 1.2%, had a mass of 81. So we'll get a couple of calculations quickly going here. And we're going to multiply 0.206 by 79, and that equals 16.247. We're going to multiply 0.782 by 80, and we'll get 62.56. And then we're going to multiply 0.012 by 81, and we get 0.972. So what this step has really done is said you're using your percentage, the original number, 78.2, and figuring out how much that particular mass is going to contribute to the average. So because we had the largest percentage here, 78.2, we multiply that by 80, and we've got a rather large 62.56 that's contributing to the overall average mass of this particular isotope. Okay, so the last step is a nice and easy one. We add everything together. All right, so I'm going to scroll down a little bit. We'll draw a line underneath all of these products, and then what we're going to do is just simply add 0.972, 62.56, and 16.274 all together. So let me quickly add those up. And we wind up with 79.806 AMU. So that represents the average mass of all of the bromine isotopes that exist. Okay, again, I want to point out that you know you've gotten to the right final answer because your original masses were in the range of 79 to 81. If you take the average of a bunch of numbers between 79 and 81, you shouldn't get a number that falls outside of that range. And the largest percentage of isotopes, 78.2%, closely had a mass of 80. So the overall average mass should be really close to the largest contributing percentage, and 79.8 is really close to the 80 mass number from that isotope.